So in this video we are going to discuss the question in thermal and statistical physics which appeared in JEST 2014 examination. So let's take a look at the first problem. The question is, for which gas the ratio of specific heats, that is Cp by Cv, will be largest. Okay, so here note that Cp by Cv ratio, Cp by Cv, it is basically the adiabatic index. Okay, so one can evaluate Cp and Cv by knowing the corresponding and average energy contribution by a individual gas molecule. Okay, so for the case of monoatomic gas molecule, so the translation degrees of freedom for monoatomic gas molecule, they are 3, and similarly the rotational degrees of freedom, so it is 0. Monoatomic gas molecule doesn't have any rotation degree of freedom, so it's only having translation degrees of freedom. So from here the average energy per gas molecule, that is equal to the degrees of freedom multiplied by the average energy contribution per gas molecule at temperature T. And this term basically it's due to the equipartition theorem. Okay, so therefore the average energy per gas molecule, it is 3/2 kBT. Okay, now for 1 mole of such gas molecule, the average energy for 1 mole, this is per molecule, and this is per mole. Okay, so that will be 3/2 kBT multiplied by the Avogadro number. Okay, and this, when you multiply the Avogadro number 3/2, that is Na kBT. So when we multiply these two quantities, the result that we obtain, that's the gas constant R. So that is Na into kB, that is the gas constant. So the average energy per mole of monoatomic gas molecule, that is equal to 3/2 RT. So from here we can calculate Cv, that is equal to dE by dt, that is equal to 3/2 R, and similarly we can calculate Cp, that is equal to Cv plus R. Okay, so that is equal to 3/2 R plus R, that is equal to 5/2 R. So from here one can calculate Cp by Cv, that is equal to 5/3 for the case of monoatomic gas, which is approximately 1.66 for monoatomic gas. So by following exactly the same procedure, one can evaluate the gamma value for the diatomic gas molecule. For the diatomic gas molecule, if we just consider one single gas molecule, okay, so let's label these x's as x, y, and z. So similar to the monoatomic gas molecule, the degrees of freedom for the diatomic gas molecule, the translation degrees of freedom, that's Ft, that is equal to 3. And this diatomic gas molecule will also have rotation degrees of freedom. It can rotate along the x-axis, y, and as well as along the z-axis. But remember that the rotation degrees of freedom along the z-axis, it cannot be excited because of the large amount of energy that's required to excite this particular mode. Okay, so therefore the rotational degrees of freedom for this diatomic gas molecule, they are only 2. So this is a situation at ordinary temperature. Okay, at ordinary temperature. Okay, so that means at ordinary temperature the total degrees of freedom, they are 5 for the diatomic gas molecule. Okay, so therefore the average energy per gas molecule, that's, now we are talking about diatomic gas molecule, that will be equal to 3 plus 2 5 into 1/2 kBT, that is 5/2 kBT per gas molecule. So therefore per mole, this is equal to 5/2 Na kBT, Okay, so that is equal to 5/2 RT per mole. So the CV value, that is equal to dE by dt, so that will be equal to 5/2 R, and Cp will be equal to 5/2 R plus 1, so that will give us 7/2 R. Oh, sorry, 5/2 R plus R. Okay, so it's 7/2 R. So therefore gamma for diatomic is equal to Cp by Cv, that is equal to 7/5, and that is equal to 1.4. Similarly, we can extend the calculation for the triatomic gas molecule, triatomic gas molecule. So in case of diatomic gas molecule, we will have Ft, that is equal to 3, and F rotational. Now the third degree rotation degree of freedom will also contribute. So in total we will have 6 degrees of freedom at ordinary temperature. Okay, so this will give us the average energy per mole, that is 6/2, so that is 3 R T basically. So giving 3 CV is equal to 3 R and Cp is equal to 4 R. So this will give us a gamma value of 4/3, that is approximately 1.33. Okay, so therefore we notice that so this for the monatomic gas molecule it is 1.6, for diatomic it's 1.4, and for diatomic it is 1.33. So with the increase in atomicity is how many number of atoms are there in a particular gas molecule. So as the atomicity increases, the gamma value decreases. So therefore the Cp by Cv value will be largest for the monatomic gas molecule. So option A is the correct one here. So let's continue with the next problem. The statement is, an ideal gas of non-relativistic fermions in 3 dimension is at absolute zero. Okay, when both number density and mass of the particle are doubled, then the energy per particle is multiplied by a factor of what? Okay, so we are given a Fermi gas at absolute zero, a Fermi electron gas at 0 Kelvin. So that means it's basically a degenerate electron gas. Okay, so as we learned in the course, the average energy per particle for the 3-dimensional, for the 3D Fermi gas, for 3D Fermi gas, the average energy per particle, that is equal to 3/5 of Fermi energy. This is one of the standard result that you must remember. Okay, now the Fermi energy is further given by, it depends upon the various parameters of the system through this relationship EF, that is equal to h cut square by 2m multiply by 3 pi square n by b and its power 2/3. So all this can be rewritten as h cut square by 2m multiply by 3 pi square n power 2/3, where small n denotes the number density n divided by b, and m is the mass of the electrons basically. Okay, so that means the Fermi energy is proportional to, if we just take a look at the parameter which are given to us, that's the number density. We are talking about the number density n power 2/3 and then divided by mass. So it depends upon number density and mass through this relationship. Okay, so now we are given that when mass is changed, so that means when the mass of the carrier or the particles, that's changed to twice the mass, and the number density n dash, it becomes twice the initial density. Then the point is that how the average energy per particle it changes. Okay, so from relationship 2, what I can do is we can correlate these two different situations. So let's say EF dash corresponds to the situation where the mass as well as the number density has been changed. So EF dash upon EF, that is equal to n dash upon n power 2/3, and then m upon m dash. Okay, so after substituting the new values of m and n dash, so that means 2n yn power 2 by 3 and then m upon 2m. So after cancellation of the common factors, so ef dash upon ef, it turns out to be equal to 2 power 2 by 3 into 1 by 2, and that is equal to 2 power minus 1 by 3. So that means the new Fermi energy will be ef dash, that is equal to 2 power minus 1 by 3 times ef. Okay, so that, okay, so this is the equation 3. So by comparing equation 2 and equation 3, equation 1 and equation 3, equation 1 and equation 3 implies that the new energy per particle, that is E by n prime, that is equal to 3 by 5 EF prime, and that's nothing but 3 by 5 times multiply by 2 power minus 1 by 3, or that is equal to 2 power minus 1 by 3 multiply by 3 by 5 times EF. So that means that is equal to 2 power minus 1 by 3 multiply by the average energy per particle in the initial stage. So therefore a factor of 2 power minus 1 by 3 will come into picture. So therefore option D is the correct one here. So let's take a look at the next problem. The question is, a monoatomic gas consists of atoms with two internal energy levels. Ground state is E not equal to 0 and excited state is E1 is equal to E. The specific heat of the gas is given by, so we are given a gas of atoms with energy levels which are given by 0 and E. You can call them as E1 and E2. Okay, the specific heat. So in order to obtain the general expression for the specific heat, we must have an idea about the variation of energy with temperature, and the energy of the system can be calculated with the help of the partition function. So the partition function for the given system is can be written as exponential minus beta E, and that is equal to, we will have only two terms here, one corresponding to energy 0 and another one corresponding to E. So 1 plus exponential minus beta E. So that's the partition function. So from the partition function, the average energy of the system can be calculated as E, that is equal to minus curly beta of ln z. Okay, and that is equal to minus curly beta ln of 1 plus exponential minus beta E. Okay, and that turns out to be equal to minus 1 divided by 1 plus exponential minus beta E, and then exponential minus beta E, and then again the differential of the exponent with respect to beta, that will give another minus E. So after rearranging all the terms, this comes out to be equal to E, and then I'm taking this to the denominator, so this will become E divided by E power beta E plus 1. So let's call this as equation 2. So now equation 2 gives us the average energy of the system. Okay, so from here the heat capacity Cv, that is equal to dE by dt, and that is equal to, let's take E outside because it's a constant value, E, and then ddt of 1 upon E power beta E plus 1. Okay, so this can be written as Cv, that is equal to E, and then differential of f by g, so gf dash minus fg dash. So gf dash will be 0 because f dash, that is differential of 1, that will be 0. So the second term minus f into g dash, minus f into g dash, so that is exponential beta E. Okay, and then the differential of the exponent with respect to t, so that will give us a term of minus E upon k t square, where k is the Boltzmann constant. Okay, and then divided by the square of the denominator, that's 1 plus exponential beta E its square. So after rearranging all these terms, so this comes out to equal to E square upon kb t square. K is a Boltzmann constant, and then exponential E upon kt. Beta is equal to 1 by kt. E upon kt divided by 1 plus exponential E by kt square. Okay, so therefore option B is the correct one here. So this is there is a little correction here in the solution of this problem. Actually, I made a mistake while concluding this result here. So we must pay attention here to the statement of the question. So we are given a monatomic gas, okay, which consists of atom with two internal energy level. Okay, the contribution of the internal energy spectra of the gas molecule, so that will be in addition to the its lateral translation motion. Let's try to understand this problem. So this is up to this point the heat capacity that we have calculated, this corresponds to internal structure of the atom. Okay, but this doesn't include the contribution because of the translation motion of the gas molecule, because the gas molecule, it can also move freely in three different random directions. So that means the translation energy of the gas molecule, one gas molecule, E translational, okay, because a freely moving monatomic gas molecule will have 3 degrees of freedom, okay, 3 translation degrees of freedom. So the translation energy associated with randomly moving gas molecule, that is equal to 3 by 2 kBT. Okay, so it's the heat capacity contribution Cv translation due to its translation motion, so that will be d E translational by dt, and that will be equal to 3 by 2 kb. Okay, so let's call this as equation 3 and this as equation 4. Okay, so therefore the net heat capacity contribution is given by the sum of equation 3 and equation 4. Okay, so that our final answer, it's not option B. Okay, it's the wrong one, it's the option C here. So again I'm repeating why we are concluding the option C to be the correct answer here, because here the monatomic gas molecule, it's not only its internal energy structure, but also it's the lateral translational motion. Okay, so this the first term, it arises from the its translational motion, and the second term it arises due to its internal energy structure. So therefore option C is correct here. C is correct. Please note it. So let's continue with the next problem. The statement is the temperature of thin bulb filament, assuming that resistance of the filament is nearly constant. So this is an important condition to solve this problem, of radius r and length l is proportional to. So okay, so we can solve this problem by making use of the power, that is the energy radiated per second, that's proportional to the the electric power across the resistor whose length is L and radius is R. So let's first try to understand that on what factor does the resistance of a wire it depends upon. Okay, so here let's assume that L with the length of the filament, or it's a simply a resistance basically. Okay, and let the cross section area of the this resistive wire, that is equal to A, and that is equal to pi into r square, where r is the radius. Okay, so that means the resistance of this wire, that is equal to resistance, that is equal to rho length, its length, and divided by the cross section area. So that is equal to rho length of the wire and divided by pi r square. So remember that r, it's a radius of wire, or you can say the filament here. Filament. Okay, so the electric, so when this filament, it's used in a electrical bulb. Okay, the power supplied to the bulb, the power supplied to the valve, that is equal to P, that is equal to V square by R. Okay, so substituting the value of R from equation 1, okay, V square and then R, so the into pi R square upon rho L. So that's the okay, it's B square, not so this comes out to be equal to pi B square by rho and then R square divided by L. That's how the power across the resistor changes with voltage and the various other factors. So this equation 3 denotes the dependence of various factors on which the power depends. Okay. Now we also know that the power, when once the wire is heated, so then it will also radiate the energy. Okay, so the power radiated by the wire once it is heated, that's the energy radiated per second, that's given by power radiated, that is equal to sigma, that's the Stephen constant, and then the emissivity of the wire. In principle it's going to be a function of temperature, but here we have given that the resistance of the filament, it's also a constant. In principle resistance, it's a function of temperature, but we will make use of this approximation that is given to us. Okay, so sigma E, and then the surface area which is radiating the power A, and then T power 4. Okay, so A is the effective surface area, which is radiating the energy. Okay, so in case of this cylindrical wire, the effective surface area will be how much? It is 2 pi R into length of this resistor. Okay, so therefore power radiated, P radiated, is equal to sigma E and then 2 pi RL and then T power 4. So let's call this as equation 4. Now under a steady state condition, we can equate the power supplied, that's electrical power supplied, that is equal to power radiated. Okay, so that means equation 3 is equal to equation 4. Equation 3 is equal to equation 4. So when we do that, we notice that sigma E into power supplied is given by equation 3. So that is pi V square by rho and then R square by L, that is equal to sigma E, that's emissivity, and then 2 pi RL into T power 4. So from here we notice that the corresponding temperature, that's related to the or the T power 4, that is equal to T power 4, that will be equal to pi and pi, they will cancel with each other in principle. Okay, so because on both sides we are having pi, so pi will cancel with pi, and one of the R will also cancel with R. So in principle I can write this is equal to V square sigma V square into R, V square R upon rho sigma E, and then what else, a factor of 2, and then it is L square. Okay, So that means, so from this equation we notice that the temperature, it is proportional to what? It is proportional to R power 1 by 4 and L power minus 1 by 2. So therefore option A is the correct one here. So let's take a look at the next problem. The question is, ice of density ρ1 melts at pressure P and absolute temperature T to form water of density ρ2. Okay, so the latent heat of melting of 1 gram of ice is L. What is the change in internal energy delta U resulting from the melting of 1 gram of ice? So we can evaluate the internal energy change by making use of the first law of thermodynamics. So according to the first law, du, the internal energy change, that is equal to dq minus dw. Okay, that's the, let's call this as equation 1. Okay, so this can be further rewritten as d, that is dq minus pdv. Okay, so now note that during the melting process, certain amount of heat is required for the ice to melt, and during this process the volume, it changes from some initial volume v1 to v2, because we know that when ice melts, its volume, it's reduced. Okay, so that means there is a change in the volume, so that means correspondingly some definite amount of work is done. Okay, so let's try to evaluate these two different quantities with the information that's given to us. So that is, what is the information that is given to us? So when ice melts, that is a process of converting ice into water. During this process, the volume of the system, it changes from v1 to v2. Okay, or in other words, you can say the density changes from ρ1 to, here it's given to be 1 gram, so this will be basically 1 by b1, and it is changing to ρ1 to ρ2. ρ2 is equal to mass, it's going to same, divided by v2, and that is equal to 1 by b2 basically. Okay, so that means in general the volume, it's related to the density through this relationship, volume, that is equal to 1 by rho, which implies dv, that is equal to minus 1 by rho square d rho. Okay, so basically we can calculate the work done either by knowing the information about dB or d rho. Okay, so from here, by making use of this result, that is equation 3 and 2, so the work done, net work done, dW, that is equal to minus or pdv here. So we will substitute the sign while putting dW here in equation 2, so pdv. Okay, when volume change from v1 to v2, or this can be rewritten as p, because the process is taking place at constant pressure, so we can take p outside, p, and then dv is equal to minus 1 by rho square and then d rho, and when the density changes from ρ1 to ρ2. Okay, so this can be evaluated to be equal to dW, that is equal to p outside. Okay, and then minus 1 by rho square, so its differential will be 1 by rho. Okay, so then with the density changing from ρ1 to ρ2, so p into 1 by ρ2 minus 1 by ρ1. Okay, so substituting the value of this result, that is equation 4, let's call this equation 4, substitute back into equation 2. Okay, but yes, we haven't yet calculated dq, so dq, that is equal to m into L, the latent heat of fusion of ice. Okay, so that is equal to 1 into L, that's nothing but L. Okay, so substitute these equation 4 and 5 in equation 2, so we obtain the resultant change in the internal energy of the ice when it's converted into water. Okay, so that is equal to L, that's dq, and minus pdv minus dw, so that is minus p into 1 by ρ2 minus 1 by ρ1. So this, after simplification, L plus P into 1 by rho 1 minus 1 by rho 2. Okay, so that's the internal energy change. So therefore option D is the correct one here. Let's take a look at the next problem. The question is, what is the contribution of conduction electrons in the molar entropy of a metal with electronic coefficient of specific heat? Okay, so we have to find the contribution of the conduction electron to the molar entropy of the metal. Okay, so we know that from the Fermi theory of a electron gas, okay, the electronic contribution to specific heat, the electronic contribution to specific heat is given as C electron, that is equal to pi square Na k square upon 2EF and then T. This is also written as gamma times T, where gamma is equal to this pre-multiplier coefficient. Okay, so this is gamma basically. Okay, now so this is equal to, this is in terms of per mole. Okay, now the corresponding contribution to the molar entropy, so that is delta S, that is equal to, let's say the temperature changes from T1 to T2. Okay, and that is dQ by T. That's a basic definition of the entropy, and that is equal to, from some initial temperature, let's say instead of writing in T1 to T2, T initial to T final. Okay, T initial to T final, and then dQ, that is CV dt upon T, and that is equal to T initial to T final, CV, it's gamma T by T dt. So T will cancel with T. Okay, so ultimately the entropy change, that is equal to gamma times T, so that gamma times TF minus T initial. If we take the initial condition, let's say at absolute 0, so then this can be written as gamma times T. Okay, but T is the T represents the final temperature. So therefore with this discussion, option A is the correct one. Let's take a look at the next problem. So we are given a situation where a 100 ohm resistor carrying current of 1 ampere is maintained at a constant temperature of 30 degrees Celsius by a heat bath. Okay, what is the rate of entropy increase of the resistor? So let's try to understand the problem here. We are having a big heat bath. Let's call this as our heat bath, which is a certain temperature T. It's going to be a very big entity having very large heat capacity. So that's the one of the assumptions that we learn when we talk about the theory, large heat capacity. So this means when we talk about the large heat capacity, so that means C, that is equal to dQ by dt. So that means when you add heat or remove a small amount of heat, its temperature of the reservoir doesn't change. Okay, so that means basically you require a very large amount of heat to change the temperature of the reservoir by a one units. Okay, so that means this heat bath, its temperature will not change for a a finite amount of exchange of heat between the any entity. So here the given entity is the resistor, which is immersed in this heat bath. Okay, and through this resistor current of 1 ampere is flowing. Okay, so a current of 1 ampere, it's flowing through this resistor, and its value is given to be 100 ohm. Okay, so the heat produced in the resistor per second, the heat produced in resistance per second, that is H, that is equal to I square R into T. T is 1 second here, so that is equal to I square R, and that is equal to I is 1 ampere, so 1 square into 100 that is 100 joule per second of energy is produced in the resistor. But remember that this energy is shared with this H, it is shared immediately with the heat reservoir, so that the temperature of the resistor doesn't change. It's given in the statement. Okay, the temperature of the resistor, it's always the temperature of the heat bath. Okay, that's 30 degrees Celsius. Okay, so that means the thermodynamic coordinates or coordinates of resistor do not change. So that means temperature doesn't change. So that is for resistor delta T is equal to 0, temperature is constant. Okay, and at the same time whatever heat is generated within the resistor, that's immediately shared with the heat bar. So that means delta S for the resistor, that will be SISTOR, resistor, that is equal to 0. There shall be no entropy change for the resistor because its coordinates or the equilibrium, or you can say it's always in the steady states. Okay, its state, it's not changing. But now the question is, what is the where is that energy going, the energy heat produced within the resistor, because that is shared with the reservoir. So for the reservoir is acquiring heat every 1 second. The reservoir is acquiring heat which is equal to or the dQ, that is equal to H, that is equal to 100 joule per second. But because reservoir it's acquiring heat at constant temperature, so the entropy change for the reservoir or heat bath will be delta Q, that's the heat acquired by the reservoir, divided by the temperature at which it is doing so. So that is 100 joule per second divided by the heat bath temperature, that's 273 plus 30. Okay, so that is equal to 100 divided by 303, and that will come out to be equal to 0.33 joule per Kelvin per second. Okay, so this is the entropy rate of entropy change of the reservoir. So entropy of the reservoir will change at this rate, but remember that there will be no change, entropy change for the resistor. It's a really a very nice example. Okay, so our answer for this problem is it's none of these, because for the resistor there will be no entropy change. So let's continue with the last problem in this session. The statement is, consider a system of 2n non-interacting spin-half particles, each fixed in position. So when each of these they are fixed in position, so that means we can treat them as distinguishable. Okay, and carrying a magnetic moment mu. The system is immersed in a uniform magnetic field V. The number of spin-up particle for which the entropy of the spin will be maximum is given by what? Okay, so here we are given the total number of non-interacting spins. Total number of non-interacting spins, that is equal to 2n. Okay, now because they are fixed, so that means it's given they are fixed, so we can treat them as distinguishable. They are fixed, so that means they are localized. That means we can treat them as distinguishable. Okay, now we assume that let number of spins aligned in the upper direction. Number of spins which are aligned in the spin aligned upward, you can say upwards, let's say that is equal to small n. So then the remaining spins, that is spin aligned downward, that is equal to 2n minus n. Okay, therefore the number of microstates for choosing n spins up out of 2n are, so the number of microstates omega of choosing small n spins out of 2n, so 2n factorial and then divided by n factorial and then 2n minus n factorials. So this represents the number of ways of choosing small n out of capital 2n. Okay, so let's call this as equation 1. Okay, so now the entropy for this system in terms of capital N and N, that is given by kb ln omega. Okay, and that is equal to kb ln 2n factorial upon n factorial into 2n minus n factorial. Okay, and after solving, so we obtain that s, we can write s, that is equal to kb 2n ln 2n minus 2n. So we are applying the Stirling approximation here, and then to the denominator. Okay, minus n ln n plus n minus 2n minus n ln 2n minus n plus 2n minus n. Okay, so now we have to maximize the entropy with respect to small n. Okay, so ds by dn, when you do that, ds by dn equal to 0, so this will result in the this equality when n is equal to n. Okay, so that means when number of spin up is equal to capital N, so therefore option B is the correct one here. So this means when the equal number of spins they are pointing upward and equal number of spins they are pointing downward, so in that case the entropy is going to be maximum. So therefore option B is the correct one here.